Good morning, everyone. I am Anupam Ojha, and I work at the Flatiron Institute, which is based in New York. I did my PhD recently with the Amaro Lab. Romy is going to talk about our stuffs very soon in the keynote lecture. Today, I'm going to talk about some of the drug discovery campaigns we have been doing over the past 7 to 10 years, and now what is the current state of research when we try to merge molecular dynamic simulations with electron microscopy. I don't need to talk about the traditional drug discovery pipeline. We all are very familiar to this. And what I want to say here is the first stage where we have the high throughput computational screening. It's the first pass, and we have very robust pipelines already there for hit to lead optimization. The real challenge begins where there are these steps where from the 1,000 to 10,000 candidates, we need to boil down to the first few candidates for trials. And that's where we have these certain problems. And this is where we want to address the bottleneck of developing systematic frameworks to refine selection and streamline decisions. So what we have identified over the past few years these are the pertaining challenges for MD simulations for drug discovery. The simulation timescale, the integration of kinetics and thermodynamics, the force field, the sampling, the automation, and how do we communicate with experiments in terms of drug design when we have these conformational sampling available. So I'm not going to talk about all of these, but I will try to cover as much as possible within the time frame here. So if we say multi-scale simulations, there's a very nice illustrative LevComs training article for our work here, where we have expanded our work from the benchmark systems, from trypsin to the HSP and the highly complex TDK inhibitor complexes. So when we talk about MD simulations time scale, let's see a very simple microsecond or a millisecond process. And if you have a computer which has a 1 GPU machine, it will take around 14 years to see one event of unbinding here, which is a very simple one-click process here. For just the helix to loop transformation in HSP 90, it takes a week to observe it on a GPU machine. So what are the quantities we care about? We care about the thermodynamics, and we also have to care about the kinetics, because if we say that a drug bind with a certain binding energy, we also need to figure out how much time does it spend at its binding site. And that's where you will hear a lot about kinetics here, the K on, the K off, the residence time, which is basically the reciprocal of K off, and the reaction mechanism and the efficacy of binding here. So why do we need multi-scale simulations? Because we care about the drug bound state, and we care about the drug unbound state. We care about what happens when a drug binds and it interacts with its residues. We care about the polarization at the binding site. We care about all of these atomistic details when we run MD simulations. But what happens if a drug is completely unbound in the solvent? Then we mostly care about the long range diffusion. We care about the association and the escape probabilities. What if I say we can run all of these different scales at once and in parallel, and saving a lot of time to get all of these quantities at once? So for example, what we have done is we have refined the partial charges of these ligands and its surrounding residues by comparing them in different layers. Like we have this MM region, we have the QM region, and then we have the QM2 region. All the residues that surround within a threshold makes the QM2 region. And now we do a QM optimized bound state ligand optimization to get the geometry and the atomic charges. And what we say here is our software called Seeker is consistently talking to the Orca simulation engine, which is what we say the QM rebind. Now we have got the partial charges at the bound state, and now we want to run simulations. But if we allow this bound state to an unbound state with a one long ergodic trajectory, it will take a very long time. So we have a lot of enhanced sampling methods at our hand, and we want to do that in a very fast way. One of the methods which works and which fits this scheme of thoughts is the Voronoi tessellations and the approach for Voronoi schemes. What you see here are the seeds, and these seeds basically form the Voronoi cell. Then all the points within a Voronoi cell will be closer to that particular seed, and the edges are called milestones. And now what we do here is we run embarrassingly parallel simulations within these milestones, and we collect the statistics to get the K on, to get the K off, and to get the delta G. What do we do Brownian dynamics for? So to get the K on, we rely on the association rate constant using the Northup, Allison, McTermott method, which is laid back 50 years back in our group. And this, what it does is, in the inner sphere, you place the ligand. It can either dissociate or associate. If it dissociates, we place it back on the sphere, and we do the association mechanism again. And with this, there's a rigid approximation and encounter-based approach, and that's how we get the K on here. So the entire maths, I'm not going to go through it, but this is how we create a transition matrix. We find the stationary probabilities of these milestones, and we get the free energy of binding per milestone, and we get the mean free passage time, which is also, I can say, the residence time of these ligands. So in the time scale of motions, what we are, or what I was worried about was, can we scale these ligands from simulations which can approximate residence time in seconds? Can we move beyond that? And can we get the ligand residence time in hours or even days time scale? Can we do that? Can we use multi-scale simulations to get a hold of the residence time, which can predict these in hours or even days? So let's look at a few of the sampling schemes we have. Let's TRMD. It is good for control polling. We exactly know what we are doing here. We also know what the ligand follows. And it gives a very rapid sampling of the scheme here. But you see that red arrow. Sometimes what happens is the ligand can also steer to the protein, and you get very, very biased energetics, or even very, very poor energies or infinite energies sometimes. And when we talk about the residence time, it's absolutely impossible to get kinetics from a distorted sampling here. So this is one of the methods weighted on sample simulation. It has its roots again in our lab back in 1996 when you have the Huber and Kim method here. What we do is we initially start with a few conformers and we let the system evolve. And we reweight, we stop, we reweight again. So it's basically an unbiased probabilistic scheme where we keep tempering the probabilities of the conformations as the system evolves. It gives you the direct rates using the Hall equation, but it's very expensive. It's expensive to the cost that it takes around weeks and even months to get a perfect sampling. But once we get it a lot. The delta G, the free energy, and the kinetics are really absolute. But the problem here are we have to keep a very high complex bookkeeping and the analysis overhead. Like you have to build a very huge size MSMs. And all of these samplings have to have a history-dependent bias as well if we want to have any bias to this. So this becomes a challenge here as well. What about metadynamics? Yes, they give you the global free energy surfaces. We get the minimums. We get the barriers. We also have a broad CV support. We can have all these combinations of CVs to bias our energies to get these flattened free energy surfaces. But what about the kinetics? Yeah, in frequent metadynamics has given some hopes in recovering the kinetics here. But then also you need to have a very good grasp of the system in charge. You need to know a lot about the parameters, the hill heights, the widths. So you know about the systems well in advance to get these rates. So what do we do? This is kind of approach where I searched for the papers that talked about the prediction of residence times using these methods. And the highest residence time it might be incomplete. And I'm sorry if that is, but these are the highest sampling, highest residence time I could find with these methods. And the sampling times are 16 microseconds, 5 microseconds, and so on. So I didn't talk about Gaussian MD because of the lack of time, but what we do here is, this is where we are. We have worked on the multi-scale milestoning methods with TTK inhibitors, with HSPs, and with the kinases, thanks to Jensen and Shinogi for their collaboration. And what we have done here is, with 3 microseconds of residence time, I'm talking about the absolute kinetics, which we get in hours and even days time scale. We have validated this over 100 complexes from a wide range of residence time, from nanoseconds to hours and days. And it is transferable, it is automated, and it is reproducible. So let's start. How does it work? So we need an initial sampling of the system here. And this is an example of a Muller potential, and we can do it in multiple ways. Yes, random accelerated molecular dynamics. You give random shots of bursts of randomly oriented forces along the CV, and you drive the transitions, you get a fine idea of what the free energy surface looks like. You can use steered MD. Fine, yeah, I know there can be issues, but if you know the systems well, you can use steered MD, or you can go for random MD, or you can use metadynamics, because what you essentially need are your seats, and these seats could be essential for driving your transitions and giving you the milestones, or giving you the idea of where to place your milestones here. Once you do that, you save these conformations along the milestones. Let's say you have 16 milestones, and you want to run 200 nanoseconds in these milestones. And that's where you do it. You run these. And once you do that, you run it parallelly. So you don't have to wait for one of the sampling to get over or to get converged. You can do it in parallel. And once you do that, you get the statistical reconstruction by constructing a Markovian matrix and getting the mean free passage time and the free energy of binding here. With this was an example of one-dimensional multi-scale milestoning. So these are the real how these milestones look like along the free energy surface. We moved from 1D to 2D milestones. Now you see these free energy surface and the path of sampling are kind of different and interesting, and the sampling is quite intense, and that's where we are right now. And let's take back again from the approach where we started. This is in 2020, where we started with trypsin, benzamidine, and beta cyclodestrine, or the host gas complexes, very common. And we started from here. With Janssen, we moved on from here to Jack, and you see the residence time approximation. You see the Spearman correlation coefficient, the R-square value. We can get insights into the thermodynamics as well. And what you see here are the transition states here. This speaks a lot about what happens about the selectivity of inhibitors here as well. For an example, if you see here, and what we found out from the milestoning simulations is we can find why a ligand sticks or has a higher residence time, because these are the contacts that can also be looked at from the milestoning simulations here. Moving on, this is one of the benchmarking complexes we thought to share, because when we develop methods, we want to work on the real complexes in general. This is a very, very, very tricky compound, because this is the loop and the hinge bind, the loop and the hinge, and they kind of are in an equilibrium, and it's very difficult for these to predict residence time very consistently over all the complexes. So just look at this one outlier. This is very interesting. I'm going to talk about it if I have time. Apart from that, the R-square value for the absolute kinetics were absolutely on spot here. Then if you look at the TTK kinases, another huge problematic complex, look at this outlier here, and I'll tell you why I'm showing you the outlier here. But if you see the approximation by the quantum corrected force field, or the approximation by milestoning methods, can give you the idea of an absolute kinetics for these complexes. So then we tried, thanks, John has given us a good talk on what S-polymer force fields are. And I was interested in having these force fields are trained on reproducing the thermodynamics. So can it predict kinetics as well using milestoning simulations? We used these force fields, and we automated the entire system. You start with a protein ligand complex. All you have to worry about is your GPUs. Once you have that, in 6 hours time scale, you can get the k-ons, the k-offs, and the delta Gs in one step. You don't have to worry about at all. What we found out was we repeated our systems, the same systems, inhibitors, TTKs, and HSPs, and you see what we get with the machine learning force field and the automated milestoning simulations here. We have got very nice Spearman correlation, very nice absolute residence time, that too in hours of time scale, 10 to the power 5 seconds. Finally, we also wanted to see what we derive makes sense in thermodynamics. And yeah, it scales directly with residence time. The low barriers will lead to fast unbinding. And the good thing is we can also associate it with secondary binding sites as well. When the ligand unbinds, it also finds some situations where it sticks with the residues out of the binding site, secondary binding site, or tertiary binding site. This gives an information about those transition states as well. And similarly with the TTK. So why I was worried about the outliers is when you pull it, you need to pull it very wisely. And because you pull it, you work on it. And the work leads to the dissipation. You need to account for the dissipation. And we worked with the Gerhard Stock group in University of Freiburg and Stephen Wolf on predicting how can we get these different unbinding pathways as well. So the outlier that I was showing you was because it had two different unbinding pathways. So we have this optimal milestoning theory. And what we do here is we get the friction profile from this unbinding, and we convert that into optimal milestones. Now we are running 2 or n multiple milestoning simulations on the same protein and get the weighted average at the residence time. So that's where we are currently. And in summary, this is what we have done. We have integrated with the most enhanced sampling schemes, discrete MD, metadynamics, dissipation corrected target MD, weighted ensemble initial sampling. The computation cost is reduced to hours. We have validated on more than 100 target complexes. Now we have, thanks to John and his group for the machine learned force fields implications on kinetics as well. And we have the end-to-end automation, residence time predictions in hours to days. And finally, we are scaling from just kinases now to GPCRs and mostly protein-protein complexes as well here. So we are developing methods and therapeutics, both. We are moving beyond the toy model systems to novel therapeutics. I'm sorry, I don't have time, but I wanted to talk about the recovering of free energy with cryo-electron microscopy, my work at the Flatiron Institute. But what essentially I would say is, let me skip all this, and we have developed a method in which what we do is we extract the free energy directly from the cryo-EM 2D images. We do not use reconstruction methods, although we go through all the machine learning processes to get the free energy profile. What I'm showing you is these perfectly nice manifolds from the cryo-EM images from the first few eigenfunctions. And interestingly, this is the free energy profile of the motions. And what I'm going to show you is, with these free energy profiles, you can get these optimal milestonings, and you can refine these free energy profiles as well, and also get the kinetics of bigger complexes as well. And finally, this is another scheme in which what we are trying to do is get the weights from the cryo-EM images, and then once you get the weights, you put that into your ensemble, reweighing any algorithm would work. And finally, what you see here is a test square of signalin. In just 2 microseconds, you have reached the unfolded state of signalin with compared to the weighted ensemble simulation, which takes around 44 microseconds to unfold completely. With this, this is the ultimate step of getting the unified pipeline with integration. We start with the sequence. You go through the multi-scale milestoning pipeline. You get the K on, K off, delta G. You refine them with cryo-EM. And finally, you end up having refined kinetics and thermodynamics for the ligands you need. I thanks all my mentor, Romy and Sonia, and Andy for them. Joachim always is there as our cryo-EM mentor, and Pilar for the mathematics behind the Bayesian ensemble reweighing. And my colleagues and mentors from different institutes, Janssen and Shinogi, for getting me started with the kinases and the TTKs. Thank you.
We have time for one question. Thanks, Anupam Ojha again. And